cosmic storm. Floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light. Riding the waves that are just out of sight.
It's the start of Season 2. Oh my god, what a season Season 1 was. Covering Nikola Tesla, gravitational lenses, the fact that birds are probably way more vulgar than their beautiful wavelengths make us think. Volcanology, the science of taste, and so much more. I also learned a ton during the season. Nothing like sticking yourself out there and just trying something. Over the summer, the show surpassed 1,000 downloads. Fun fact about podcasts, there are tons of them, many of them. Well, at least more than 4.5 million currently registered podcasts and another 30,000 every day. Fun fact, 90% end by episode 3. And out of that 10-ish% that continue, another 90% end by episode 20. Meaning Whimsical Wavelengths is already in the top 1%. So there's lots to build on. As a startup science podcast, being able to crack in the top 50% based on downloads of all podcasts is a great first step in Season 1. Personally, summer was great fun. The hiatus is now over. Over the summer, I went camping with my kitten, who is fast becoming a cat. He loves it, by the way, with his harness and leash, chasing bugs and making noises at birds and squirrels. He is otherwise an indoor cat, in an effort to not feed the local coyote population and to protect the whimsical birds. I also got married, survived having children without school to keep them occupied. It was a wonderful and busy summer, juggling everything, including my day job as a geophysicist. During all this time, I was also preparing for this, Season 2. Trying to think of a way to get the show out to more ears, thinking of mechanisms to improve sound quality, get more guests, find more science stories to tell. We'll see how all of that goes as we move forward here in Season 2. Remember, don't forget to write a review on Apple or rate me on Spotify. I'm beginning to understand that those reviews are huge to help others find the show. It's also much more likely that they'll get suggested to someone when they look for something like science podcasts. For the first episode of Season 2 here on Whimsical Wavelengths, I figured I'd do a solo. Okay, not that type of solo. I'm going to go ahead into one of my papers. I only have so many of those left because I've been doing the industry thing, but perhaps I'll get my name on a few more in the future. Future teasers. That should eventually come to pass. We'll see how the rest of this season comes together. Perhaps there'll be a few more teasers yet. Because it's one of my papers, that means heading back to volcanology. Like other historical scientists covered here on Whimsical Wavelengths, I was attempting to follow where the data was pointing, following the path. When I was planning my PhD, yes, I was in the envious position of basically picking my projects. I knew I wanted to do more at Masaya Volcano. During my master's, I collected a bunch of geophysics that unfortunately didn't tell a big enough story to be published on its own. But I learned a lot working with other team members. The hydrothermal system with Dr. Guillaume Marie. Gas geochemistry with my PhD supervisor, Dr. Glynis Williams-Jones, and Dr. Tricia Nadeau. Can't forget Dr. Hazel Reimer and fellow student at the time, Dr. Guillermo Cavalcantes, and others. Basically, after a long day collecting data in the sun and the heat, we would get back to base and drink some beer brainstorming the system. Maybe it was the heat that was addling our brains, but we would sit there and spin tales of what it is, what it was, what it will be. Perhaps I should get the gang together with beers and play that game again. Some of the best scientific ideas came out of that kind of stuff. Of course, most of them were terrible, but every once in a while there's that gold nugget that comes out and you can write an entire scientific story around it, find the data and follow it down. Sadly, the local situation in Nicaragua had gotten worse, so my old group hasn't been back since. You know, working in some places is its own discussion. So, the volcano. Masaya Volcano is a shield volcano located in Nicaragua. Its magma comes from the interaction of the Caucasus Plate subducting beneath the Caribbean Plate. The Caucasus Plate is a small oceanic plate, much like the Juan de Fuca Plate, that subducts to form the Cascade volcanic arc. As the Cocos plate is subducted into the mantle, it heats up and releases water into the hot mantle above it. Like salt added to ice, the water in the mantle lowers the melting point of it, and magma is formed. If that magma manages to reach the surface, we have a volcanic eruption. That's the 10,000-foot discussion for the vast majority of subduction-related volcanoes around the globe. Masaya is special. Yeah, it's a unique volcano in many ways. At this point, I went back to the literature and was overwhelmed with nuance and different ways to describe what makes Masaya Volcano special. For the moment, I'll settle on two things, and I'll layer in a bit more as we go. Masaya is persistently active. It's been in a perpetual state of unrest for hundreds of years. The last eruption of any significant amount was 1772, where it produced a lava flow from its central cone. Since that time, there's been lots of degassing, the occasional lava lake, and small vent-clearing explosions. There's not many volcanoes on Earth able to claim constant activity for hundreds of years. Oh, and number two, it can have Basaltic Plinian Eruptions. Basaltic Plinian Eruptions. For those who know a little bit about volcanoes, this may seem like an oxymoron. First, though, I think it's best if we explain and define Plinian eruptions. For that, a short historical deviation to ancient Rome. Damn it. There it is again. Guilty of thinking of the Roman Empire. A callback to the end of Season 1 with the rise of leaded gasoline, a running joke perhaps? All roads go through Rome. So, the year is 79 AD, and Vesuvius is erupting in a cataclysmic explosive manner. Pliny the Elder and his nephew, Pliny the Younger. Glad we don't do that anymore. Jeff the Younger? It was bad enough when I was working on Masaya Volcano. Everyone was calling me Jeffycito, or Little Jeff, I guess. Where was I? Pliny the Elder was a Roman author, naturalist, and natural philosopher who died during the eruption of Mount Vesuvius. His nephew's account of the eruption and how his uncle died during it while trying to rescue people from the disaster is the reason we categorize these eruptions as Plinian. Love a good origin story. A Plinian eruption is characterized by powerful explosions that send ash and gas high into the atmosphere, forming distinctive mushroom-shaped clouds. There are associated hazards like ashfall, pyroclastic flows, and lahars. For Pompeii, it was a pyroclastic flow right at the tail end of that flow that caused the destruction and the deaths of the people there and getting frozen into the poses that they were in. That story and TikTok of events that led to the preservation of that city and the people is a story for another day. So back on track, let's go through what is normally required for a Plinian eruption. First, we need high amounts of gas or volatiles. This mostly means water, carbon dioxide, and or sulfur dioxide. Perhaps longtime listeners will remember that gas is the primary driver of volcanic eruptions. Yes, it needs enough heat, etc., but if there's no volatiles, magma will be denser than the rocks around it and have no upward force. To be clearer, gas gives an upward force within the Earth. Once it reaches close to the Earth's surface, you no longer have that confining pressure from all the rock above it and around it. And once that confining pressure is reduced enough, we have enough force from the volatiles, and those bubble walls that they've created can fail, because that gas is now pushing outwards in all directions, and as that fails, the magma begins to fragment, and that fragmentation then to that fine powder and that very strong force in kind of all directions, but mostly still up, is what creates a Plinian eruption. So just to quickly summarize, more gas, more force. More likely, the eruption will be explosive instead of effusive. Yeah, another term. Effusive means erupting lava onto the Earth's surface without large explosions or explosions of any sort. The second important part of whether or not an eruption is going to be really explosive is viscosity. If magma or lava has low viscosity, it can allow the gas or volatiles to escape without exploding violently. Think of water. The higher the viscosity, the harder one needs to blow to create bubbles. It's harder to blow bubbles in honey or toothpaste than in water. Water has a lower viscosity. It doesn't resist flow. So viscosity is actually a little more complex than just a simple number. There's many factors that determine how lava flows and how much resistance it provides due to force. For instance, lava and magma are non-Newtonian fluids, meaning the characteristics of the flow or the viscosity is stress or force dependent. To be fair, we probably all had some of this experience in our everyday lives, especially if you're old enough to use a glass bottle for dispensing ketchup. Trying to get just the right amount out isn't always easy. Apply a little force to the bottle, and all of a sudden the ketchup viscosity drops and it comes out too fast. Water, on the other hand, behaves under most circumstances as a Newtonian fluid, which maintains a constant viscosity with increasing force. To give an example of a non-Newtonian behavior in an eruption, it's easiest to look at highly viscous lavas that are relatively gas-poor. They'll effusively erupt, or better word, extrude, onto the Earth's surface through spines or towers. Their viscosity is so high, at least to begin with, that they don't flow. They just come out as a big, plug. And as they come out, they tower up on each other. And it's only when they are high enough, they have enough weight at the top that they can flow. Let's try that description again. Imagine squeezing out a paste vertically, and it comes out straight up. And it will continue to come straight up until there's enough mass stacked up through this paste that the bottom has enough force to start to flow, where that viscosity is reduced because of the force. Just like the ketchup example. Okay, before I get way off track into viscous or silicic domes, I think what we need here is the term or a generality. What we're really looking at is how materials deform and how these materials flow. And that whole study of material flow is called rheology. Viscosity, flow, rheology are all important for the upcoming whimsical episode in hopefully 2 weeks' time. I may have to correct this later. For completely different reasons. What makes a magma or lava more viscous? Well, it's chemistry, structure, gas, and temperature. These are all the primary ways to change viscosity of a magma. Let's start with the most important, chemistry. Well, any change that changes chemistry can change viscosity. We're just going to focus on the most important part of the chemistry, silicon and oxygen. When they're in the melt, they act like a polymerizer, forming chains and networks within the fluid that increases the magma's viscosity. It makes it so the magma sticks together more, resists flow. In fact, the basic categories with respect to all volcanoes are based on the amounts of silicon and oxygen, and therefore viscosity. Basalt, for instance, 45 to 52% is silicon oxide. Basaltic andesite is 53 to 56%, andesite 57 to 63%, dacite 63 to 69, rhyolite is 69 to 75. I also listed them with increasing viscosity, increasing silicon and oxygen, increasing viscosity. For the same gas levels, the rhyolite is going to be more likely to be explosive than the basaltic andesite. So we can predict a range of eruptive behavior based on chemistry. On to temperature. Well, being cooler increases viscosity. To borrow a phrase from the Sam Roberts Band from the song The Canadian Dream, everything moves real slow at 40 below. I guess this is the second musical call-out of the episode. This is also conceptually understood in the kitchen, or via grease and oil, or cars and automobiles if you prefer. The heated oil and grease flows easily, cooler and it doesn't flow so well. This happens to water too. It gets more viscous when colder. Lava or magma is no different. Cooler lava has a higher viscosity. A cool basalt can definitely erupt more violently, but typically we think of these as like Strombolian eruptions. They are explosions. You do not want to be near an eruption like this. But it isn't going to be like a Mount St. Helens or Pinatubo or Krakatoa. The temperature on its own isn't going to change into a basaltic magma into a Plinian-style eruption with pyroclastic flows and, destroyed the famous Pompeii. It needs something more. We're almost ready to circle back to Plinian eruptions and their dynamics, but we still have two more factors, and that's what's in the magma: crystals and gas. With respect to gas or volatiles, it's complicated. Generally, though, increasing the gas levels reduces the viscosity. There is nuance and some interesting things that happen around the edges that are not really required to explain anything here. Quick aside, though. Do you ever wonder how we know some of this stuff? One part is definitely measurements in the field, going to active volcanoes and making observations and building data. One part is model and math-based, where we put everything into a computer model and see what shakes out. The largest part, though, is really analog models, creating magma in a laboratory set up under specific conditions and measuring different attributes. Sometimes, though, real pouring of molten material, and sometimes in temperature and pressure-controlled apparatuses. A volcano in a box, if you will. Finally, for this discussion, crystals. Magma is not just one chemical. It's a soup of a whole bunch of elements and compounds. Much like if you put salt into water and evaporate it, eventually, the salt concentrates, reaches a saturation point, comes out of solution, and crystallizes. We can think of magma as similar, but instead of evaporation, it's temperature controlled. As the temperature drops, specific minerals become stable and begin to form from the melt. For viscosity, this has two effects. First, it's changing the chemistry of the melt. Having a mineral that has less silicon and oxygen in its crystal structure than the amount in the melt effectively concentrates it in the leftover what's left. It's removing all the other elements. If you've ever taken a geology course or perhaps a geography course, I'm dancing around explaining Bowen's reaction series. This explanation is process-based, so I won't get into the individual minerals, so on and such forth, but it is an important name drop for anyone wanting to look up more about this process and explore it. The second thing it's doing, as temperature drops, is the crystals themselves. They're going to increase the viscosity. Think a Slurpee or a slushy, an icy, watery slurry, or a fine mix of the two. It's going to have more resistance to flow than just water. The more crystals, the higher the viscosity. Summarizing the logic here that was at the heart of one of my chapters of my PhD thesis, Masaya Volcano erupts basalt, which is pretty much always low viscosity, meaning it has a hard time to create large explosive eruptions like Mount St. Helens or Vesuvius. The magma or lava is just too fluid, and the volatiles can escape too easily. It just can't build up enough pressure to be able to fragment the lava and create or have enough stored energy to create these Plinian eruptions. So why do we see pyroclastic eruptions in the rock record from Masaya Volcano? The rocks are there. They're of basaltic chemistry. We can see the structure and the grain size. We can see the ash. We know it happened. That story, piecing together that scientific inquiry, would be fascinating to dig into beyond just the peer-reviewed literature. Before I digress too far, I decided one way to tackle this problem is to go and probe the chemistry of the system. Yes, was a geophysicist, but sometimes you need to change the type of data to continue the search for a solution. What's the answer? Geophysics on its own couldn't get me there. I really wanted to answer the question of how you ended up with basaltic Plinian eruptions, where it can erupt more magma in an explosive way than the 1980 eruption of Mount St. Helens. I really wanted to understand this behavior, so while there was an extensive work looking at the whole rock geochemistry, I thought maybe, just maybe, I can get a glimpse into the magma chamber through melt inclusion geochemistry. The chemistry of the whole rock shows the eruptive lava of the entire system. All of the eruptions are chemically stable for many tens of thousands of years. That chemistry, though, is the result of all processes that have taken place from the moment the melt is formed till it erupted. If that material just before eruption hung out in the shallow magma chamber for many hundreds of years, or tens of years, then the eruptive whole rock can't tell you very much about deeper processes. Yes, you can get at it and hint at it through things like trace elements, but you're missing a lot. So enter melt inclusions. Already stated that magma, as it cools, will begin to form minerals. As those minerals form, they often do not form perfectly. They can have variable growth rates on different parts of the crystal. It can be a fairly chaotic system. So often, while growing, they can trap bits of the magma they're forming in. These blebs or bubbles can then freeze into glass upon eruption, entrapping a snapshot of the magma at the time the melt inclusion was formed. So, here on Whimsical Wavelengths, we're keeping it glassy. Though it pains me to say it, we need to shatter the flow for a moment and explain the glass transition temperature before things get too brittle. Magma, or lava, as it cools, it can reach the point where crystal development is actually impossible. And the liquid is too viscous, it can no longer flow. The material is crossed its glass transition temperature. Glass is not a crystal. It's an amorphous solid lacking any sort of crystalline structure. And there's lots of different glasses around in the world. Not all of them are silicon-based, like what we're talking about here in reference to volcanoes. This whole topic is important because, for two reasons, one we'll circle back to eventually, but in this particular instance, glass in a perfect melt inclusion contains the whole chemistry of the magma when it formed. This includes the volatiles or gas in solution. So ideally, that melt inclusion provides us a snapshot when it was formed about what the chemistry of the magma was. Including the volatiles. That's huge. And ideally, the crystals, or at least the melt inclusion, spend different amounts of time within the magmatic system of the volcano at different depths. So let's imagine that we have a magma chamber at a particular depth, and the magma spends a lot of time there. We're going to get a clustering of the melt inclusions formed within that magma chamber. If there's multiple magma chambers, then we should see that kind of evolution as it changes depth and temperature, as the chemistry within that melt inclusion should start to change. And it will change through the residence time it spends within the Earth, within that magmatic system. With melt inclusion geochemistry, we also need to know the chemistry of the host crystal. And there's lots of different ways I can tackle this, but I'm going to just stick with olivine in this particular instance because it's the favorite of these types of studies. Olivine, like many minerals, does not have a single formula. Instead, we say it has a solid solution series, which is the compositional range between two end-member minerals that share the same basic chemical formula, but experience substitution of elements in one or more atomic sites. Olivine is preferred because it forms fairly early, it is stable for a long period of time, and has low diffusion across the crystal, which just means that it doesn't lose. Different elements can't go across the crystal easily. And that's a whole other discussion that I'm going to leave here for the time being. When olivine forms early in the magmatic system, it's typically closer to one end member in its solid solution series called fosterite. We give it a shorthand in volcanology and describe it by stating the percentage or fosterite number, where the higher number should be closer to the mantle chemistry. So melt inclusions hosted in olivines closer to fosterite or having a higher fosterite number likely had less time to change and evolve, and therefore more likely to have a true concentration of the source, including the volatiles. I thought I could collect samples from each eruptive feature within Masaya's caldera, crush the rock, pick the crystals, find the melt inclusions, and gain the information to tell three important things: the depth to the magma chamber, information that may lead to understanding of what conditions are necessary to bring about basaltic Plinian eruptions, and pre-eruptive volatile levels, i.e. how much gas are we really talking about in this system. So, the process of getting the crystals. The pain. Even when I think back now, it was quite the ordeal. So, in my samples, every single one of them, there was approximately 1% or less olivine crystals. And they were quite small. Dark green crystals in a sea of black and slightly rust-colored glass. I'm sure, in fact I know, there are better ways to do this with fancy solutions, picked for the right density, so that way you can just let olivine crystals settle all the way through and catch almost everything else out. But I didn't have access to much of those, so first I crushed the sample. Because you want to free the crystals from all the glass, but you don't want to crush it so much that you break the crystals. My department had a machine that does this, but my samples were pretty breakable. They were scoria, they had lots of holes, very easy to crush it. So I just used a mortar and pestle, so that way I could just do a little bit of material bit by bit instead of having to do a whole bunch of sample in one go and then lose some control about how much I'm crushing it. Once I had several cups of crushed material, I put it into a gold pan and panned away the lightest of all the material, which is usually glass. The olivine and other crystals like feldspar and pyroxene and the denser parts of the glass without so much vesicles are then concentrated at the bottom of the gold pan. With the leftover material, I'll put it in a petri dish and put it under a microscope with the light from above and below. The water and the light made it easier to find the crystals because the light would go through the crystals of the minerals that I could use. There was also magnetite, which I could not use, but that was more just annoying because it would keep sticking to the metal tweezers I was using to search and remove the crystals. Many hours staring at bright lights through a microscope to find crystals. Once you have them, then it's time to mount them in something so that way it's possible to sand or polish into the crystal face. Using sandpaper grit and a microscope, first you gotta polish it until the crystal is intersected. Normally it was hard to see if there was any large melt inclusions until this point, unless the inclusion was quite large or the crystal was quite clear. I should add, I also had so few olivine crystals, and it took so long to find each one, that I wanted to test each and every one, because picking them out was such a pain in the... If there is a melt inclusion, then slowly and carefully I sanded down until the melt inclusion was intersected, and then polished it. Once prepared, and as soon as I have enough of them, it was time to hit them with wavelengths to determine what elements were inside, trace elements and the like, as well as the volatiles. And I did this at Clermont-Ferrand in France, and I got to do the volatile Raman spectroscopy in Lyon, France. Chemistry-wise, unfortunately, the melt inclusions provided nothing new. All the samples fit or agreed with the whole rock. Better constraints on how the system evolves, but nothing outside of the norm that was already known. But that, in itself, is surprising. The whole rock and the melt inclusions are pretty close to coming from a single batch of magma, i.e. there's no evolution in the system, right from melt inclusion to the whole rock. That's weird. I mean, look at Hawaii and Kilauea. These are eruptions with different chemistries that happen quite often. They're quite distinct from one another. Even though a volcano like Masaya is nearly always active, everything's the same. Volcanoes that have persistent activity, we typically think of them as having a complex magma system. Not all the magma interacts with one another. They have different pockets of magma in different places, allowing for different temperature cooling histories and therefore different chemical evolutions, leaving distinct magmatic chemistries upon eruption. Like, we can actually see this in the whole rock as well as the melt inclusions. So Masaya whole rock and melt inclusions suggest everything came from the same process. There is no differences in evolution of the different eruptive features within the caldera. It suggests a really simple magmatic system where everything travels through the same way. It's thermally buffered. And this is really important because changing the temperature, as I already said before, changes which minerals will form or will be stable. And therefore, as they come out of the solution of the magma, the resulting chemistry of the melt normally changes. But in this instance, it's all the same. Okay, so that's the chemistry. Another thing we can get by probing the melt inclusions is volatiles. How much is actually in the magma? If we assume the highest concentration is the undegassed amounts for an individual gas, like sulfur dioxide, then we can look at the glass in a sample to find out how much is still in the lava after it freezes. Wait, I think I just skipped a part. In addition to going and polishing all the crystals and trying to intersect all these melt inclusions, some of the sample was sent off for a thin section. A thin section is a slice or a standard thickness of the rock, which will have crystals, the glass, the air bubbles, even some crystal, like right through the middle of crystals, are all in this thin section. It's important to know that basically always, especially with basalt, lava erupted to the Earth's surface will cool faster than it can form crystals. There will almost always be material that goes through its glass transition temperature, locking in all the stuff that's left over into a glass. And this is really important because whatever's left over in that melt will also include volatiles. Well, I probed the crystals and found what I believe to be a maximum sulfur dioxide and hydrogen chloride concentrations in the melt. And these two I feel pretty confident because they only degas when the magma gets really close to the Earth's surface. However, carbon dioxide and water, they begin to degas fairly deep, especially carbon dioxide. So let's just assume I have zero control over how much carbon dioxide that I have. There's some games we can play with it, but it's not really important to this story. Water, the maximum I found was about 1.5 weight percent, and I did play some games with water and the like via volatile balancing, but the bigger takeaway here is that the sulfur dioxide, using the amount found in the thin section glass, so that's the amount that's locked into the lava afterwards, and the maximum in the melt inclusion, we can get a total expected degas amount. Basically take the maximum concentration we have and minus how much is left over in the glass after eruption. Masaya is also an easy volcano to get to. You could call it a drive-in volcano. You can drive right to the summit crater in the center of the caldera. There is, or at least was, lots of measurements about how it degasses. And I was able to take that data and estimate the total amount of sulfur dioxide erupted over the measurements. We know how much per unit volume of lava we need to create a specific amount of sulfur dioxide because of the melt inclusions. So if we know how much has degassed over that time, and we know how much is in the magma, we can calculate just how much magma needed to be degassed over those measurements. And it worked out to be 7 cubic kilometers of material. Yeah, that's like almost double what Hawaii has produced in the last 40 years. And it's actually quite flabbergasting to be quite realistic about it all. And it goes further than this. This volcano has been in a perpetual state of unrest and basic constant degassing since its last effusive eruption in 1772. Now, this part isn't correct. There's huge air bars and everything else, but if we assume the same degassing budget over the whole time since its last eruption, or effusive eruption, that works out to being over 40 cubic kilometers of magma that is degassed, but not erupted. That's crazy. That's crazy. I mean, yes, you have to acknowledge the huge air bars and the caveats with this number, but like how? Where does it all go? Well, going back to the chemistry, if all eruptions for tens of thousands of years have similar chemistries, they need a way to be all the same. What process can get that done? The best I could come up with is there must be a deeper magmatic system where all this material goes. There must also be a tectonic mechanism that's allowing space to be created. I mean, if you're going to bring up 40 cubic kilometers of material but then don't erupt it, you gotta put it somewhere. I mean, these types of dynamics are studied at Kilauea and Mauna Loa in Hawaii and a few other volcanoes due to their size and other things that are creating space at depth. In the case of Kilauea and Mauna Loa, their flanks are mobile. There's so much weight that they're actually causing them to move. And that's going to create areas of lower pressure and create space within the crust. And for some talk about this, please check out Season 1, where I went into detail on Mauna Loa and how the whole rift zone had reorganized, likely due to large mega landslide or debris flows. Here in Masaya, though, the best I could come up with was pull apart faults or grabens. So the Managua graben, which is one of these instances, it's a bit like a rift zone in some respects. The crust is thinning or pulling apart, and one end of this fault or graben ends at Masaya Volcano. And it is quite possible that the crustal thinning or pulling apart will allow for storage of material at depth. Or at least this is what I settled on to explain the problem that we have possibly 40 cubic kilometers of magma that hasn't been erupted. It has to go somewhere. So the summary, Masaya has as much flux from the mantle as other persistently active volcanoes like Kilauea or Mount Etna. But it doesn't erupt it. Its chemistry is stable over many thousands of years. The magma system must have an open and easy connection to a deeper magma reservoir, deep enough that we can't see it at the Earth's surface. So magma comes up from this deeper reservoir, degasses, becomes denser, and sinks back down again. The constant movement from shallow to deep and new material, hot material, creates a system that is thermally and chemically buffered. Pretty good results. Not to toot my own horn too much. But what about those Plinian eruptions? Well, I got very little in my results to help explain that behavior. Yeah, the results give a pretty good idea about the state of the magmatic system before, but it doesn't give us anything about a trigger or other change to point to, nothing. And unfortunately, I couldn't continue down this road. I had to call it quits because I wasn't able to work and stay in academia and follow this down. That doesn't mean that other people have just let this scientific inquiry stop, because it's a really interesting subject. It's a really interesting thing, and others took it up, and I'm so glad that maybe they've gotten to the right answer. Going back to our discussion of viscosity. So we know the chemistry doesn't change. So there's no reasonable mechanism to explain where a large increase of gas would come from. If there was a huge pulse of new magma into the system from deep beneath from the mantle, you'd be able to see its chemical signatures. And so without that, you need to look more at viscosity instead of gas. And the logical place to look is the other factors to do with viscosity: temperature and crystals, and the glass transition temperature. The temperature where the lava or the magma becomes brittle, or if you want to we could say it this way: as you approach this temperature, the viscosity increases very quickly. The idea or hypothesis works like this. You get a large volume of magma beneath the Earth's surface, probably fairly shallowly in the magmatic system of Masaya. So the whole system is cooling. It's forming lots and lots of small crystals as it goes through this. It's also getting closer to its glass transition temperature. It's starting to become viscous. Pressure builds as the gas in there must expand. Eventually the pressure becomes too much and the whole system fails. The magma fragments, and depressurizing causes a runaway effect of the gas expanding faster than the magma can flow out. So it explodes, breaking little bubble walls in the magma. Boom! The whole cascading of the system goes until that shallow pockets of magma are all erupted, creating a collapse caldera. How Masaya Volcano's magmatic system enters that state, we don't know. But once there, it makes physical sense. What really bothers me about this, though, is that we have no idea about the precursory activity to expect. Most of the time, before a large Plinian eruption, we get months of unrest before the cataclysmic phase of the eruption. Masaya is always in a state of unrest. There are also hundreds of thousands of people that live on the edge of the caldera, like literally on the rim. Masaya City is built on one caldera edge. This story is so much more than just academic thought. There's real implications to understanding this. Well, there's Season 2, Episode 1 in the books. Please give the show some lava. Rate it, review it, tell people. Share the social media posts. There isn't many podcasts out there that do what Whimsical Wavelengths does, and none with this kind of pizzazz or a certain je ne sais pas. Yeah. So, with that, expect episode 2 in 2 weeks. Until then, adios.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's all waves. Colors weave stories painting the sky, swaying to rhythms as the galaxies fly by. Seeking